Example 2. Determine the features of the rational function. F of x is equal to x cubed minus 2x squared plus 3x divided by 2x squared plus 2. So let's try to be systematic here. The first thing we might always find is usually the easiest, the y-intercept. That's f of 0, and that'll be 0 minus 2 times 0 plus 3 times 0 over 2 times 0 plus 2, which is 0 over 2, which is 0. And so our y-intercept is actually the origin. That actually turns out to be an x-intercept as well, but we'll keep going here. The next thing that we should look for are the critical values. P of x is the numerator, which is x cubed minus 2x squared plus 3x. I want to know, when does that equal 0? That's going to be a factoring or polynomial problem. So everything that we were doing in chapter 3 is kind of the first step in chapter 4. We can factor this, and this is x times x squared minus 2x plus 3 equals 0. So either x equals 0 or x squared minus 2x plus 3 equals 0. This one is done. We're good there. X equals 0 is one possibility. That's our one critical value for the numerator. For the other one here, you might think that this factors. It actually doesn't factor very well. We're going to have to use quadratic formula here. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And in this case, we'll get 2 plus or minus the square root of 4 minus 4 times 1 times 3 all over 2 times 1, which is 2 plus or minus the square root of negative 8 over 2, which is 2 plus or minus 2I root 2. Remember to simplify those radicals, or the root. So these are complex and are not x-intercepts or roots or real roots for P of x. And so in rational graphing problems, which is what we're doing, those can be ignored. These can be ignored here. Not in general, but in this problem, they can be ignored. Okay. The other critical values are going to happen when q of x equals 0. Q of x was equal to 2x squared plus 2. That was the denominator. And that'll equal 0 if 2x squared is equal to negative 2, or x squared is equal to negative 1, or x is equal to plus or minus the square root of negative 1, which is I. And these are also complex and can be ignored. So we have one critical value. So let's talk about what that means. Well, what do the critical values help us find? They help us find zeros, x-intercepts. And in this case, f of 0 actually equals 0. So 0, 0 is an x-intercept. It helps us find vertical asymptotes. But f of x, sorry, q of x is never equal to 0. So there are no vertical asymptotes. That's because these guys were imaginary. These roots were imaginary. This means that there are no vertical asymptotes. The only value here that was x equals 0 that gave us 0, that result was right here, the x-intercept. And then finally, there are no holes in the graph, as there are no values of x for which f of x equals 0 over 0. So there's not a whole lot of distinguishing features on this graph. What do we know? Basically, we know one thing. This passes through the origin. That's about all we know so far. But I say that's all we know. It passes through the origin, but we also know there are no holes and no vertical asymptotes. So this is an example when you don't have any vertical asymptotes. The other thing that we can get from our critical values, and I should have actually done this first, was the domain. F of x is undefined for no values of x. That's also related to this result here. And so the domain is all real numbers on this problem, which wasn't the case in the last example. So the domain is all real numbers. We have an x-intercept that also doubles as our y-intercept, and we have no holes or vertical asymptotes. So pretty boring overall, but we can do some more analysis. Now it's time for us to look at end behavior. So what happens as x approaches plus or minus infinity? What happens on the left and right endmost parts of this curve? Well, we can do some analysis there. F of x was equal to x cubed minus 2x squared plus 3x divided by 2x squared plus 2. And in this particular case, as we classify this, the degree of p of x, the numerator, is 3, and the degree of q of x, the denominator, is 2. So one of our rules that we talked about last week was if the degree of p of x is greater than the degree of q of x, there is no horizontal asymptote. Instead, this result means that there's what's called a slant asymptote. This means slant asymptote. Well, this means our asymptote is found using long division. So what we're about to talk about is using long division to find the slant asymptote. We had done an example last week. Let's do another one here. Here we're going to do 2x squared plus 2 divided into x cubed minus 2x squared plus 3x. But I'm going to change this form. We actually want to rewrite this as 2x squared plus 0x plus 2 divided into x cubed minus 2x squared plus 3x plus 0. So we're going to use placeholders so we don't make any silly mistakes. And I would also note here that I can't use synthetic division because of the form of my divisor. It's not linear. It's not x minus c. So here we go, really quick. Let's review some of that. Putting it all together. 2x squared times what is equal to x cubed? That's going to be a 1/2 x. And as we distribute this here, we're going to get x cubed plus 0x squared plus x as we multiply by each term. And then we'll subtract. And we'll get negative 2x squared plus 2x. Now for my next round here, we'll ask ourselves 2x squared times what equals negative 2x squared? Well, that's a -1. And then we'll do the same distribution. And we'll get negative 2x squared minus 0x minus 2. And I guess we can bring this 0 down. Plus 0. Parentheses subtract. And then we'll get 2x plus 2. And that is our remainder. This is degree 1. It is now less degree than what we're dividing by. This is our remainder. And what we have is, let me do this in black, f of x, which was x cubed minus 2x squared plus 3x, divided by 2x squared plus 2 is equal to negative 1/2 x minus 1 plus a remainder of 2x plus 2 over 2x squared plus 2. And I can clean that up just a little bit. This is 1/2 x minus 1. And if I factor a 2 out of the top and bottom, I'll get x plus 1 over x squared plus 1. So this is my alternate form of f of x. Now this requires you to do some analysis and use your thinking cap. So now the question is, oops, for end behavior, as x approaches plus or minus infinity, what does f of x approach? Well, let's analyze f of x. f of x equals negative 1/2 x minus 1 plus this x plus 1 over x squared plus 1. Now, we've talked a little bit about this before. As x approaches positive or negative infinity, the remainder term should approach 0. So what's happening is we're plugging in very, very large numbers. And because this is our remainder, because we know this is our remainder from the long division, let's analyze this. Since the remainder is found when the degree is less than the divisor's degree, so the fact that this 1 here was less than this 2, that told us that that was our remainder. Now, when we come back down here to our form, this is going to tend towards 0 because the denominator is growing faster than the numerator. Since the degree of x plus 1 is less than the degree of x squared plus 1, the denominator will grow faster than the numerator. and the value of the fraction will decrease. And as they say, tend towards 0. So in the long run, as x approaches in plus or minus infinity, f of x will approach just the quotient, 1/2 x minus 1 plus 0. That term there is going to 0. And so this is the equation of our slant asymptote. Y equals 1/2 x minus 1. So let's actually take a look at that behavior really quick. I'm going to show you what this graph looks like. I thought I had Desmos open. Desmos, let's see. Yeah. So this is our graph of the function f, or y, equals x cubed minus 2x squared plus x divided by 2x squared plus 2. And if I actually put the asymptote in here, let's see, y equals 0.5x. Oops, no, sir. Back up. 0.5x plus 1. Oops, minus 1. Dagnabbit. Minus 1. What we see here is, and I guess it's not too hard to see, but maybe purple would have been not the ideal choice there. Can I change the color? I guess not. Stuck with purple. Anyway, what we can see is the blue curve here is the actual rational function, and the purple curve, or the lower curve there, if you can't really see the difference between those two colors, is the asymptote. And what happens is, as we go out to positive or negative infinity in either direction, on the ends, the left and right extremes, you can see that these two functions are behaving in the same way. So that's what this notation means. Let me actually just draw it again for you guys really quick here. Let me draw this in red. So a y-intercept of -1, and then a slope of 1/2, which is up 1/2. It's going to look something like this. This is y equals 1/2 x minus 1. And this is our slant asymptote. And it turns out that if we graph this, let me get a good color here. Purple, I guess. If we graph this sucker, we know we have our x-intercept, and we know that we have to start hugging the asymptotes. And so our curve looks something like that. The question is, while we're getting arbitrarily close to this asymptote, we now wish to determine if, as x approaches positive or negative infinity, is f of x a little above or below the slant asymptote. Okay, so let's do some more analysis. As x approaches positive infinity, f of x is equal to 1/2 x minus 1 plus this remainder of x plus 1 over x squared plus 1. And we have f of x approaches 1/2 x minus 1 plus 0. We know that as x approaches positive infinity, x plus 1 over x squared plus 1 approaches 0. But the question is, it's even though it's getting close to 0, it's not exactly 0. Is it a small positive number or a small negative number? And so since we are using positive values of x here, this is x plus 1 over x squared plus 1 is positive over positive. And so this is actually 0 plus, meaning that as x approaches positive infinity, f of x approaches the line 1/2 x minus 1, but is slightly above or greater than 1/2 x minus 1. This term on the end isn't 0. It's really small and it's close to 0. But in this case, it's positive. And so this curve is doing the following. It goes through 0, and then it starts to hug this asymptote, and it stays on the top side of the asymptote. Now, as x approaches negative infinity, f of x approaches 1/2 x minus 1 plus this term that's going to 0. But for x plus 1 over x squared plus 1, as x approaches negative infinity, this is going to be negative infinity plus 1, which is a negative number, divided by negative infinity squared plus 1, which is a positive number. So this is tending towards 0, but a little bit less. Now that takes a lot of practice, folks, and you're going to want to practice it, but that means here then, as x approaches negative infinity, the graph is just below the slant asymptote. Which means two things are going to happen here. For the other side, let me just use a different color here. Let's see. For the other side, it's going to get close to the asymptote, but it's going to have to finish on the bottom side. So this finishes below the asymptote. While the right side finishes above the asymptote. But it also means this, and this is something that students probably aren't used to unless you get into this class. How many different highlighter colors can I use to make this convoluted? This curve crosses the asymptote. F of x crosses the asymptote. So this graph has the feature that f of x crosses its slant asymptote. Now, the question then is, where does this occur? So let's take a look at that. this will occur when f of x equals the asymptote. So our function was x cubed minus 2x squared plus 3x divided by 2x squared plus 2. If I set that equal to the equation of the asymptote, I might be able to find out where this point is. So we can find this by setting the function equal to the asymptote and solving for x. And that's exactly what we're going to do below. Multiplying both sides by the denominator, we have x cubed minus 2x squared plus 3x is equal to 1/2 x minus 1 times 2x squared plus 2. Foiling out the right side, we're going to get an x cubed minus 2x squared plus x minus 2. And we can see that, oh, that's a terrible choice.
Could you move up a little bit, please?
Yeah, for sure. Is that enough, or you want me to go more?
No, that's enough. Thank you.
Okay, yeah, for sure. We can subtract x cubed and negative 2x squared from both sides. And what we're going to get is the equation 3x is equal to x minus 2, or 2x equals negative 2, or x is equal to negative 1. This is the value of x where the curve f of x crosses its asymptote. Now, if you want the actual ordered pair there, all you have to do is either, since this is a point on both the asymptote or the curve itself, just plug x equals negative 1 into either function. So f of negative 1 is equal to negative 1 cubed minus 2 times negative 1 squared plus 3 times negative 1 divided by 2 times negative 1 squared plus 2, which is going to be negative 1 minus 2 minus 3 divided by 4, or negative 6 over 4, which is negative 3/2. By the way, you'll get the exact same value by plugging it into the asymptote, and it's actually quite a bit easier. Same y value. So coming back up here, so this is the ordered pair. Negative 1, negative 3/2 is where f of x crosses its asymptote. So I know you guys are frantically trying to write this down. I'm just going to scroll up really quick. I'll come right back to this. This is the point negative 1 comma negative 3/2. And that's where it crosses the asymptote.